Okay, so we come to lecture number 2. This lecture we're going to deal with classification, which is another branch of machine learning. So last time we saw regression, in a simple case, linear regression. So then we're going to look at what's called classification. And so classification is distinguished from the regression in that our response variable is not just a real number. It's rather it's a category, or what we can call it a label or something. So last time we had data vectors. So there were some vectors in a d-dimensional space. So they're d tuples of real numbers. So each data vector xi is a d tuple of real numbers, like here. And we had for each data vector we had a response, which is just a real number. And the idea was to try to fit a linear function, of this form here to our data here. But now we're going to look at the case where these yi's are not just real numbers. So they're not real numbers, but rather sort of categories. So here we also last time what we were doing was this loss function again, which was a function of the parameters of the betas in this case. So here now I guess I got too lazy to call them betas and call them b's. And so what we have is that we are given the data points here, the data vectors. They're fixed, and then we're varying the coefficients, the b's, the b0, b1, b2, and so on, in order to minimize this loss function. And we did this by using a gradient descent last time. So in the classification part of it, we don't allow our y's to take any value. We only allow it to take a finite number of values. So we're going to be particularly interested when we only can take 2 different values. So we're going to take these 2 values to be +1 or -1. So now an example of such a thing would look like this. We have here we have our data vectors here on this axis here, and then there are only 2 values that can take. So each data point here can take either the value +1 or it can take the value -1. So that means that we probably are going to try to divide our data vectors into 2 sets, those that have the +1 and those that have the -1. But if we try to fit a line to this this data here, well, that's going to be pretty bad, because I mean, you see points out here, they're going to be very far away from any line you try to fit this to. It's not going to work very well, because they're I mean, lines. If you take an x value here, you can sort of, as by moving the x value, you can get any y value here. But our y values only are 2 of 2 kinds, +1 or -1. So a linear regression here is not going to work very well. So the idea is to try to do sort of a linear regression, but then try to take these values and squash them into a range where we can deal with them. So the idea here is that well, let's maybe just set up the problem for us. So we are trying to try to train a model. So we're given a set of training values. That means we have vectors, training vectors, and for each of these training vectors we have a label, either -1 or +1. And so what we're trying to do is to create a model such that when we get a new data point, data vector, then the model can tell us whether that should have label +1 or -1. So that's in this case, a binary classification problem. You can also have more than 2 values, but we won't be looking at this right now. So here's a sort of a figure here that shows what we're dealing with. We have a set of, in this case, 2-dimensional data vectors here, and they're labeled. Some of them have +1s, and the yellow ones have a label +1, and the purple ones have label -1. And so what we're trying to do is we're trying to create a model that separates these 2 sets of data points, such that when we get a new data point here, say out here, then the model will tell us, is this data point, should that be labeled +1 or should it be labeled -1? And the way we're going to do this is by trying to find this dividing curve here that divides the plane into two sets, those that have +1 and those that have -1s. And so given a new data point, if we get a new data point, we can see which side of this curve does this data point lie on, and that'll be the prediction of the model. So basically, the categorization or the classification problem in the case where we only have 2 categories is to try to divide the space of data vectors into 2 disjoint pieces, so that we can use those to predict when we get a new data point, data vector. So for now, as I said, we're only going to deal with the case where we have two labels, and there are. This is actually I would say the real most common problem in machine learning is a classification problem. This is where there are many different models for doing this. So it's where most of the deep learning or most of the machine learning problems are in this field of classification problems. So we're going to look at a model that's called a logistic regression model. So it's called regression, but it is in fact a classification model. And so the idea is to sort of take what we talked about last time, namely the regression model, and see if we can turn that into a classification model. And the idea is to take the values on the line, so the y values on the line, and then apply a function to them that squishes them into the interval between 0 and 1. So if we squish things into an interval between 0 and 1, then we will call such a point between 0 and 1, we'll call that a probability, because that's where probabilities, they live between 0 and 1. And so our idea for classification is apply this function to our line, squish the y values into probabilities between 0 and 1, and then we'll classify by saying that if this probability we get, if it's bigger than a half, then we'll give it label +1, and if it's less or equal to a half, we'll give it label -1. So that's how we turn a regression problem, a linear regression problem, into a classification problem. So in order to squish these y values into the interval between 0 and 1, we're going to use what's called the logistic function. And I have written it here. So it takes a real number z, and it turns it into this value 1 divided by 1 plus the exponential function of -z. So this is in fact a number that's always between 0 and 1. So you can see the exponential function is always positive. So the denominator is positive, numerator is positive, so the whole thing here cannot be negative. It will always be between 0 and 1 because this here is positive, so we're dividing by something that's bigger than 1, so we're smaller than 1, and again, we can't be negative. So this is a function that, in fact, does what we want. It takes the whole real axis, all the real numbers, and squishes them into the interval between 0 and 1. And the way this function looks is here. Here's the graph of this function. So you can see here that it takes values that are negative. They get very small values, because if you have a negative value, so here we have, let's say we have this number here, minus 10. What's the value of the logistic function? Well, it's 1 divided by the 1 plus the exponential of minus 10, so that's plus 10. So the exponential 10 is a pretty big number, and so we have a large denominator here, and so this will be a small number. You can see here it's very close to 0. Similarly, if we take a positive number here, plus 10, well, what is the value of the logistic function? Well, we put a minus here because it's x1 divided by 1 plus x per minus z, so it's x per minus 10, and x per minus 10 is a very small number, and so we have 1 divided by 1 plus a very small number, and that is 1 plus x per minus 10 is close to 1, so we're close to 1 divided by 1 equal to 1. So out here we're close to 1. On the negative side we're close to 0. At 0, when we're right here, what is that? Well, that the value of the logistic function is 1 plus x of 0. X of 0 is 1, so it's 1 divided by 2. So at 0, the value of the logistic function is precisely a half. So this is sort of the dividing line here, where the value of the logistic function is a half. So you can see that that this z, when z is positive, it's going to have a value of the logistic function that's out here, so it's bigger than a half. Down here, it's going to be a value smaller than a half. So here's the code that graphs this logistic function. So the idea is that we're going to take each of our data vectors, and we want to associate to that some real number. Then we're going to apply the logistic function to that real number, and then we're going to check if this value is bigger than a half or smaller than a half. And so that will be the way we classify a data vector. So we have to find a way to assign a real number to each data vector, and that's exactly what we did last time. We're going to use regression, a linear regression, to do that. So we're going to try to find coefficients beta 0, beta 1, and so on, such that when we get this value z here and take the logistic function of that is going to match the labels we have for our training set. So our training set, again, consists of labeled data vectors. Each data vector in our training set has a label either +1 or -1. So we're trying to find these betas here such that when we take this z given by this expression, you apply the logistic function to it, then we're going to get if the label of this x here, if that is 1, then we want that sigma of z should be bigger than a half, because that would label it to be +1. If the label was -1, then we want this sigma of z to be less than a half. So that is how we're going to train our model. We're going to use the outcomes of this, applying this this logistic function to the values of this linear function. So that's how we're going to train our model. So again, what we need is a loss function. So last time the loss function, well, that was taking the difference between the y values and try to minimize the squared distance here. But now we don't have any y values anymore. All we have is plus ones and minus ones. So we can't quite do that. So we're going to do another thing, and that is a loss function, which maybe looks pretty strange. So here is the loss function for logistic regression. So the loss function, again, it's a function of the parameters. We want to minimize the loss function in terms of these parameters. We want to find these parameters that minimizes the loss function. Now the loss function looks strange here. So the yi's are the labels, so they're plus ones or minus ones. So we have here this thing I call z. So this thing here is the logarithm of the logistic function applied to the label yi times, let's call it zi. So zi is this linear expression here. So what that looks somewhat weird here, right? That's not clear what goes on here. So why are we interested in minimizing this function? What good does it do to minimize this function? Well, let's try to look at it and see why that is interesting. So let's look at a data vector here. That's xi. Here are the components, xi1, xi2, xid. And so if we're given some coefficients, beta 0 and so on, we can compute this as zi here. So suppose the label of this data vector xi is plus 1. So it's a data vector in our training set, so it has a label. And what would we want then? Well, in order for the model to correctly predict that, well, then we would need that sigma of zi should be bigger than a half. And what would that mean? Well, that would mean that zi should be positive. That's what we saw. The sigma here takes positive numbers into values of probabilities that are bigger than a half. So you want zi to be positive. Now so this is the case here where yi is plus 1. And so that's the same as saying that yi times zi is, this is annoying, is positive. And so that means that that the log of sigma of yi ci is, why does it keep doing that? Is what? Well, yi times ci is positive, so sigma of ci is bigger than a half. That means that log of this is bigger than log of a half. But since we're taking minus in our loss function, so it's we can see here it's minus the average of all these logarithms. So that would mean that we get that the contribution to the loss function from this log sigma yi ci here would be less than minus log of a half. Now, if in the other situation where yi is minus 1, Well, what do we want then? Then we want that sigma of Ci should be less than a half, because that would mean that the model predicts a value of -1. So what would that mean? Well, that means that we want the sigma of what? We want sigma of Ci. Well, we want the Ci to be less than 0. But that means that yi times zi should be positive. So again, we get the same thing here. We get that yi zi is positive. There's something wrong with this stuff here. This is. So we want, in all cases, we want this yi times zi to be positive, because that's gonna give us the correct classification of the data point xi. So if this again is positive, we have this thing here. So that means that the more correctly classified points we have, the more of the terms are going to satisfy this condition here. And so that means that we're going to have lots of terms that are smaller than minus log a half. And so we want to have lots of points where the value is less than minus log of a half, and that will give us lots of correctly classified points in the training set. And so that's why we want to minimize this. The more points we have that have small values, that means we want the loss function to be small. So we want to minimize this loss function. So this is a bit of a long-winded explanation of that. The loss function can be somewhat difficult to understand. So you should think about this argument here. I've written it out here in some detail here. So you just think about why this makes sense. So we want to minimize this loss function. So again, we can try to do gradient descent like we did last time. So that means we have to compute partial derivatives of this function here with respect to the parameters. That means with respect to the betas. So to do gradient descent, how do we do it? We take the value of these parameters, subtract a multiple of the gradient, and that gives us our new updated set of parameters, and we iterate this many times. So this does involve computing the gradient with respect to these betas. So we need to compute these things here. So again, the loss function is a sum of these terms, of these log terms. So taking the partial derivatives of the loss function, well, that's just taking the partial of each of the terms and then summing them up. That's not the hard part. The hard part is to compute the derivative of these terms. So they are of this form here: log of sigma of z. So sigma of z was 1 divided by 1 plus x per minus z. So what we're looking at is, well, log of 1 over something is minus the log of the denominator. So it's minus the log of this. So I'm going to use the chain rule here because this is a composite function, right? It's composed of log and sigma and the argument to sigma is yi times zi, and zi is a function of the betas. So this is a sort of a very nested composite function. But we can deal with that because we have what's called the chain rule. So here is how we're going to do the partial derivative of this function here. So at first, it's the function, it's a derivative of the function with respect to the zi of this function here, and then multiply that by the derivative of zi with respect to beta. So this is a chain rule that hopefully you have seen or can refresh your memory. If you don't remember it, then refresh your memory and try to get it. So let's do the two pieces here. So let's do what's in the box here first. The other one here is simple. We'll do that later on. But let's do the thing that's in the box here first. So this again, this is a composite function composed of the log function. Inside the log function, we have a 1 plus the exponential. And then inside the exponential, we have the function minus yi times zi. So it's a function of zi. It's composed of three functions. So let's see what we do here. First, the derivative of the log function. Well, the derivative of log of x is 1 over x. So that's what we get here. First, we get the derivative log. We have a minus in front of it. That's what we have here. But take the log and take the derivative of this. That's 1 over this thing here. Then we have to multiply that by the derivative of this thing here. So, well, the derivative of 1, that's 0. The derivative of the exponential function, that's the exponential function, times the derivative with respect to zi, what's in here, and that's minus yi. So altogether we have the minus we had out in front, and then we have the minus coming from here. They cancel to give a plus 1, and so the derivative of what's inside the box here is given by this thing here, yi, and then in the numerator x for minus yi times zi, and in the denominator 1 plus x of minus yi times zi. So that was the first part here. The second part, well, what's the second part? The derivative of the second part is very easy because zi as a function of the betas is just given by this. So if we take the partial with respect to a beta k here, well, if we take the partial with respect to beta 0, then all the other ones are going to give 0. It's just going to be the derivative of beta 0 with respect to beta 0. That's a 1. So if k here is the first one, if it's 0, then we're just going to get 1. If we're up here, then we have beta 2 times xi 2. And so taking the partial with respect to beta 2 is just going to give us this thing here. So the partials of the z with respect to the betas is very simple. But altogether, we're getting some pretty nasty looking formula for the partial derivatives here. So the partial derivatives of the loss function are given by these horrible looking expressions here. Now it turns out they're not that bad as one can figure out here. You can do it a little bit easier. You can take this expression here, you can divide it through by x minus yi times zi, then you're getting this thing here. So in fact, it's just sigma of minus yi times zi. So it's not that bad, and what you can see here is that you're having this factor here is the same for all the k's here. So it's really not terribly bad. We're going to get this expression here. We're taking this factor here and we're multiplying it onto the vector, the data vector, but we had to put a 1 in the first coordinate here. So it's just computing this term here, and then multiplying that onto the data vector with this 1 added in here, and then averaging over these things. So that's a gradient of this loss function. So it looks pretty scary, but in reality, it's not so bad. Not so bad at all. So what can we do with this? Suppose we have found this minimum of the loss function. So that means we have sort of created a model that in some sense classifies correctly as many points as possible in the training set. It may not be able to correctly classify all of them, but at least it will be it'll do the best possible job that we can do with this model. So let's look at what's going on in the sense that if we look at the set of points where so we have found these betas here. Let's say we've minimized the loss function. We have found these betas, and so let's look at the set where this z is 0. So where beta is 0. And so we're looking at all the points in RD such that this is 0. So this is what's called an affine hyperplane. If we like to deal with just the plane, which we do because we can draw things there. It's nothing but a line in the plane. But this line divides the plane into two pieces, into two disjoint pieces. Those where this value here is positive, and those where it's negative. And so there where it's positive, we're going to get a classification of -1, and for those that where it's negative, we're going to get the classification of +1. So it's a little misleading here, but that's the way the logistic function works. So we have sort of achieved what we were set out to do. We have found a line. So in the case of the plane, it's a line, and in higher dimensions, it's this affine hyperplane, which we can't really draw. But we have found we've done what we set out to do. We have found a way of dividing the space of data vectors into two pieces, one that's classifying +1s and the one that's classifying -1s. So that solves this problem here. It defines a model that does the best possible job on the training set. And so the next question is, how well does it predict? And so to do that, we're going to look at an example, but here's just sort of a picture of what we have done so far. Here's here's a sort of a toy data set. It's not a real data set, but it shows here that we get a line which divides the plane into two areas here. One where most of the ones that in the training set that are labeled -1 lie here. There might be some the other ones here, the ones that are labeled +1. There may be that there are a few points that are not totally correctly classified. So we might on this line we might get some of the points in the training set here. These will be misclassified because the model would classify them as -1s, but they should actually be +1s. So, anyway, the minimizing the loss function does give us the best possible fit for this data set here. So let's look at we call this the hyperplane. We call this the separating hyperplane, and whatever. That's not so important. So let's apply this to a